So I am the Purnomo. Currently, I'm a postdoctoral researcher at the UC Berkeley. At the UC Berkeley, I'm working on the wildfire modeling for fire at the wildland urban interface. But what I will be presenting today is my work in my PhD, which is the simulation of wildfire, but at the peatland that consider both flaming and smouldering. This work is the collaboration of Imperial Health Lab and researcher from Belgium and researcher from Indonesia, Research Center for the Sensing. This is the outline for the presentation today. Firstly, I will briefly introduce the topic. Then I will continue with the objective of the research. After that, I will explain how the model was developed and how we obtain the data needed for the model. The next part will be the validation of the model and results and discussion, which will be wrapped up by the conclusion. As we know, wildfires happen all around the world, from tropical to Arctic landscapes. Wildfire can happen in various ecosystems such as savanna, grassland, shrubland, rainforest, and peatland. And when a wildfire happens in a peatland ecosystem, it can release gigatons of ancient carbon and create a positive feedback to climate change. This wildfire can also cause hundreds of thousands of premature deaths due to the diseases infected by its emission, such as respiratory and cardiovascular diseases. Moreover, it is projected that the frequency and severity of these fires will increase due to the change in populations, land use, and climate. This is an example of peatland wildfire that happened in Indonesia in 2018, which was coincidentally happening near our location around 2 hours of driving when our group, Imperial Health Lab, conducted a field study in Indonesia. The two main observable characteristics of this fire are, firstly, the smoke that keep coming although there is no more flame, as we can see in the video. And secondly, the smoke that stay in a low altitude and can travel to the populations. This phenomena can be explained by using this figure. Wildfires are typically started by flaming combustion that consume the surface vegetation. This flaming sweep the surface vegetation and could ignite the soil underneath. The soil remain burning for weeks to months via smouldering, although flaming has disappeared. This phenomena cause the smoke that keep coming although there is no more flame. This video shows a closer look of flaming of pine needle and smouldering of soil from peatland. Compared to flaming, smouldering is flameless, has lower temperature that make the smoke from smouldering can stay in a low altitude, and smouldering spreads much slower to order of magnitude and make the smouldering remain active for a very long time. How does the soil in peatland ignite in the first place? The soil in peatland is dominated by peat. Peat is a carbon-rich organic soil, and this type of soil is formed by partially decomposed organic material, which are mostly plants that are accumulated over many years in waterlogged, anaerobic, acidic, and nutrient deficient condition. It is kind of a baby coal, where it can become coal if there are enough pressure and time. Therefore, peat is combustible. In 2018, we had the opportunity to do a field scale experiment on peatland wildfires. We did the experiment in Indonesia, in Sumatra Island, during the summer. One of the experiment was smouldering peat that are ignited by flaming of surface vegetation via slash and burn. As we can see in the figure, the flaming was initiated on the north side of the plot with 10 meter by 10 meter size. The flaming burned the litter or dry surface vegetation on top of the ground. After the flaming extinguished, we investigate the smoldering ignition on the pit using visual and infrared camera. If we look at the topography of the plot, we see that the plot is not flat. The north side of the plot is lower than the south side. This will correspond to the measurement result that we got from the cameras. From the investigation, we found that the ignition of smoldering pit is not uniform. The ignition was concentrated at the south side of the plot, where from the topography, it is higher ground. Because the ground is higher at the south side, it is therefore farther from the ground water table, which means that the pit at the south side is drier than the north side at the surface. As we know, moisture content is the single most important factor that affects smoldering. So drier pit means favorable for smoldering. Having said that, the ignition at the south side of the plot is also not uniform. I like to call it a polka dots pattern because there are patches of smoldering ignition. There are many factors that determine the ignition, such as mineral content, rocks, and so on and so forth. So even though the moisture content at the south side of the plot is similar across the width of the plot, the probability of smoldering ignition is not similar over the width of the plot. The moisture content of pit in the peatland vary both spatially and temporally. The spatial variation in vertical direction is relatively simple because the closer the pit from the groundwater table, the wetter it becomes. The figure on the right show the pit moisture content at depth. So 30 centimeters means 30 centimeters below the surface. Meanwhile, the spread variation on horizontal direction, such as one in the left figure, is significantly more complex. This is because the variation is affected by many factors, such as topography, surface vegetation, and root system. Complex variation are also observed temporally, where the temporal variation of pit moisture depend on many factors, such as hydrological processes, weather conditions, seasonal change, and climate change. From those facts, understanding peatland wildfires mean understanding of physical phenomena. We're talking about thousands of hectares of landscape that involve flaming and smoldering combustion, and both are affected by environmental factors that also vary spatially and temporally. Therefore, experimental study on its actual scale is very expensive. For instance, the field study that we did in Indonesia in 2018, in total can cost $10,000. So the alternative would be computational study. Of course, firstly we will look into physics-based model. However, this is tremendously expensive. By using high-performance computers, it could still take days to simulate the fires over a short time. And if we are talking about peatland wildfires, we are talking about wildfires that can sustain for weeks, even months. There is an alternative approach in computational study, which is called cellular automata. And this method is significantly cheaper than physics-based model computationally. So it is suitable for peatland wildfires modeling. The objective of this research is to understand flaming and smoldering wildfires on peatland via simulation of CA or cellular automata. Cellular automata are discrete mathematical models that use simple and flexible rules. CA limit the execution of only within small area around the point of interest, which is called a neighborhood. GA is more like a computational strategy or framework. Therefore, developing CA model is similar to developing behaviour or farsight from the scratch instead of modifying part of the existing model. The model that many people are familiar with is like changing the radiation equation in GPARO or FTS for certain cases, or adding urban fire model to farsight. But in CA modeling, it can be imagined that the model itself does not exist yet. So we must be thinking the same way as the developers when they firstly start developing the models, like Chris Stottenberger or McFinney when they start developing behaviour or farsight. Well, we did literature review on CA for fire modeling. In this figure, what is Fleming wildfire model? Gray is smouldering wildfire model. Blue is urban fire model, and green is building fire model. There have been many CA models to simulate wildfires. There are many different rules have been used depending on the phenomena that want to be captured. In this figure, the bold font highlight the pioneer of each rule. The rules that are used can be categorized as stochastic, that have uncertainty, and deterministic, that does not have uncertainty. Of this model, only few are used for smouldering, and the only CA model that simulates both flaming and smouldering wildfire in Peatland is our previous work. In this work, landscape scale Peatland wildfires was simulated. However, this model does not consider the variation of peat moisture content, and the model was not validated against observation. And inspired by this work, we advanced the model to include the temporal variation of peat moisture content and validate the model against satellite observation. To simulate peatland wildfire that involve flaming and smouldering, a multi-layer approach was used as shown in the figure. So it's like in MATLAB, if you use MATLAB, it's like there are two matrix variable, one for soil and one for surface vegetation. The flaming occur in the surface layer and can ignite the peat in the soil layer. The ignited peat then spread through the fill bed of peat in the soil layer. However, the addition of flaming vegetation from smoldering peat is not considered. So the transition from smoldering to flaming is not considered because of lack of data and scientific knowledge on the phenomena. The model consists of 5 steps: the surface vegetation SV, flaming vegetation FV, exposed peat EP, smoldering peat SP, and burn peat BP. Exposed peat correspond to the failure of ignition of smoldering peat by flaming vegetation. So not all flaming vegetation cell can ignite the smoldering peat, and when the peat is not ignited, it becomes exposed peat. We use 2 layers of soil automata, so 2 metric variable, surface and soil layer. And the model starts with the flaming vegetation that make nearby surface vegetation transition to a flaming vegetation with a probability of PF. The flaming vegetation can also ignite smoldering peat underneath it with a probability of PT. And the smoldering peat can make the nearby exposed peat transition to become smoldering peat with a probability of PS. And finally, the smoldering peat become burn peat with the probability of PE in the next time step. The values of the probability for the models are obtained by using calibration. So the model will run when we get all the probability value, and we find those values using the calibration. The calibration in both flaming and smouldering probability start with calculation of the speed rate. For flaming, the speed rate is calculated based on Rotemel model, and for the smouldering, the calculation is based on the interpolation from experiments. After we calculate those two speed rates, we select the domain size, which is quantified by lambda, spatio-temporal resolution. Lambda is just the cell size divided by the time step. An example of different lambda is shown in the figure at the bottom, where with the same landscape size, the size of cell are different. By considering this spatio-temporal resolution, we can use any cell size and time step for the model that corresponds to any spatial and temporal resolution. Then we choose a probability value and run the model. If from this probability value that we choose, the speed rate in the model is not close to the calculated speed rate, the probability value is changed until the condition is met. So it's like a optimization. When this rate condition is met, we select another lambda, and we do this to make the model is domain independent. So it's not affected by the domain size and time step. So after we get the domain independent model, we can use the model for any spatial and temporal resolution. A new lambda need different probability. So the probability calibration is performed again and again, and we select different lambda and recalibrate the probability until many different value of lambda. So the point is that we choose one lambda, find the probability until it matches the speed rate. Then if it matches, we choose one lambda until many different lambda. So we are sure that the model can be run in case the spatial or temporal resolution are different from the one that we use in the calibration process. There are two steps to determine the PF or flaming probability. First, the determination of initial flaming probability. In here, we call it flaming base probability, the y-axis of this figure. And the second is the determination of the flaming probability after considering the wind effect, which is the value of PF itself. The determination of flaming probability of the initial flaming probability is based on Rotemel equation with zero wind condition. We found that this probability, the figure, has a power correlation with the speed rate, which is shown by the linear correlation in the log axis. This power correlation prevails for many different lambda or spatio-temporal resolution. And with different lambda, their slope are equal. This initial probability is multiplied by the wind factor that was derived based on Huygens wave propagation principle. However, there is a side effect of doing the multiplication, and a wind factor is to be compensated by using a correction factor that also depends on the wind speed, and shown in the red figure. So when we multiply the base probability with the wind effect, the correlation becomes not simple, and then there must be a correction factor to make it match again with the expected value. This shows the complete equation for the flaming probability from the previous calibration. F, or the final flaming probability, has a power correlation with the Rotemel speed rate R, and also a function of wind effect alpha W and vegetation density factor alpha V. The wind effect is formulated as the product of the rothermal wind speed, capital VW, correction factor from the previous figure, psi, which is the angle between wind and fire, and theta, and the ellipse parameter A, B, and C. The equation of the ellipse is adapted from the Kepler law for orbital of planet, which also follows the ellipse trajectory. What do A, B, and C represent in the ellipse? This figure illustrates the formulation of wind factor. The red square is the origin of the fire. A, B, and C are the semi-minor, semi-major, and eccentricity of the ellipse. Theta is the angle between the fire direction and the wind direction, the beta. The A, B, and C are the function of the wind speed as shown in the equation, which is adapted from the work of Alexander. So it also used in far side. For smouldering, we use experiment of ignition probability and smouldering spread on different peat moisture content to determine the transition and smouldering probability. For the PT, or the transition probability, we directly use the correction from the work that it is inversely proportional to the peat moisture content. And for the PS, the smouldering probability, we translate the spread rate of smouldering at different peat moisture content into a probability value for a different domain, or for different lambda, or spatial temporal resolution. This translation is performed by simulating one by one probability value at different lambda to make the spread rate in the simulation match with the spread in the experiment. This shows the complete equation for the smouldering transition and the spread probability derived from the calibration. The Fleming to smouldering transition probability has an inverse exponential correlation with the moisture content. This is the same as the one mentioned in the work of Franzen. Meanwhile, for the smouldering spread probability, or PS, it has an inverse power correlation with the moisture content and the spatial temporal resolution, or lambda. For the smouldering extinction probability, or PE, it was selected with 5 times 10 to the power of -10, which make the smouldering can sustain for around 3 months, which is the typical wildfire season in Indonesia. Wildfire season duration in Indonesia. The model is firstly verified if the split rate in the simulation for both Fleming and smouldering is close to the expected value when the model used different spatial temporal resolution. We found that the split rate in the model for both Fleming and smouldering are similar with the expected value within 20% difference when using many different spatial temporal resolution. We used the model to simulate a Peatland wildfire in Borneo, Indonesia, that happened on 21st of September 2018. This fire was fully extinguished on 10th of October 2018. This figure shows the progression of the Fleming wildfire captured by the Sentinel-2 satellite. The black color in the figure represents the burn scar, whereas the red areas represent the regions of flames. The light green color represents the non-combustible region, like a fire break or burn area that resulted from previous wildfire, but not considered in these regions. And the dark green is the combustible vegetation. The data from the satellite image were used as validation data on the burn scar for Fleming. For the input, the first data that we consider is the vegetation type, which will be used for the Rotherman equation. We classify the vegetation type to be wet shrub, dry shrub, and trees, following the work on the land cover classification in Borneo. We also consider fire break that correspond to the non-combustible fuel. We determine this type from the landscape analysis on the satellite image, in which fire breaks can be indicated by the abrupt stop of flaming wildfire. So the edge of the burn scar looks very smooth, which is unlikely. The fire break can stop the flame spread, but for smoldering, they assume that smoldering can pass through the fire break because it can spread underneath the fire break or underground. The second input for the model is the vegetation density. We use NDVI or normalized difference vegetation index that quantify the greenness of the surface. So higher the NDVI value, the greener the surface. So it can be used to estimate the density of the vegetation. To simplify, we classify the density to be only three categories. We found that the NDVI of the landscape range from 0 to 0.65. We split this range to be three ranges from 0 to 0.2 that corresponds to recently burned, and from 0.2 to 0.4 that correspond to the regrown vegetation, and from the 0.4 to 0.65 that correspond to intact vegetation. Regrown vegetation is the vegetation that was burned in previous wildfires, but already regrowing, although not fully regrown yet. So it's like a baby vegetation. The vegetation density factor for the intact vegetation is set B1, whereas for the recently burned is 0 because this is close to bare soil. And the factor for the regrown vegetation is set to be 0.01 obtained from the calibration. For the weather, the first input is the wind speed and direction. The figure shows the wind speed and direction, which is indicated by the direction of the arrows in the location during wildfire. So from 21st of September 2018 and for 20 days. We got this data from BMKG, Indonesian Institution for Weather Forecast. We also consider precipitation or rains, which also from the BMKG. And this precipitation affect the sustainability of flaming, and this is quantified by the probability of flaming extinction. So the higher probability of flaming extinction mean the shorter lifetime of flaming, and this is formulated following the work of Alexandridis. The next input for the model is the peat moisture content. So we use catchment land surface model, CLSM, to estimate the moisture. CLSM rely on the hydrological process and topography consisting the distance from groundwater table, interaction with vegetation and roots, solar exposure, precipitation, and other hydrological processes. Our collaborators from Belgium developed a peat-specific CLSM prior to this research, and we use that improved model to estimate the peat moisture on daily basis. The main difference between the original CLSM with the improved model is that the improved model consider microtopography that represent the small-scale hill and valley that are typical to peatland. This improved model shows high accuracy in the peatland, especially in tropical countries. This figure show example of monthly average of peat moisture content in different years obtained from the peat CLSM. The validation for flaming was based on the burn scar obtained from the Sentinel-2, and for smoldering validation, we use algorithm developed by another collaborator of us that distinguish between flaming and smoldering hotspot. This algorithm rely on several satellite bands, such as shortwave infrared, and perform arithmetic operation to distinguish between flaming and smoldering. The algorithm was validated against ground observation that was conducted on several islands in Indonesia. But this was also developed prior to this research. This figure shows the smoldering hotspots, the yellow circle, obtained from the algorithm. However, we only consider the number of smoldering hotspots rather than the shape of the smoldering for the validation of our model. This indicates that we validate the model based on only the ignition of smoldering without considering the spread of smoldering. We did not validate the spread because smoldering can occur undetected and even in the subsurface. So the detection result from the satellite or algorithm can be not valid. This is the simulation results of Borneo peatland wildfires that start on 21st of September 2018. It is a search of 50 meters and time step of 20 minutes. So with the spatial temporal resolution of 150 meter per hour. In this animation, white is surface vegetation, brown is exposed peat, gray is fire break, red is flaming vegetation, and yellow is smoldering peat. In the first few days, flaming wildfire are present while also initiating smoldering hotspots. And after the flaming wildfire extinguished, the smoldering hotspots remain active and growing bigger. On day 3, after the start of the wildfire, flames burn a relatively small area of surface vegetation, and the shape of this burn scar from the model is cylindrical, with non-smoothness at the perimeter caused by the stochastic approach of the model. Compared to satellite observation, the red line in the right figure, the prediction of overestimate the lateral spread, where in the observation, it shows an elongated shape. This discrepancy means that the effect of wind in the real event is stronger than the simulation. However, this discrepancy is relatively small. On day 8, the western wind caused the flames spread dominantly to the east, which is stopped by the fire break. The low vegetation density on the north side of the burn scar caused an unburned patch. Smoldering hotspot began to form at this stage. The elongation of burn scars because of wind in the observation is more clear in the stage, which is the main source of error for the prediction. And on the 20, all the flames had become extinguished. And we believe that the extinction of the flame corresponds to the 14.7 millimeters of precipitation that continues for 3 days. So there are a little bit heavy rain on those days. And at this stage, the nucleation of smoldering has stopped, but they still continue to grow via smoldering spread. The burn scar from the prediction has a good agreement with the observation, as we can see in the right figure. We stop the simulation after 90 days. At this stage, the smoldering hot spots, the yellow color, we show the legend. The yellow color that were previously too small to see become large enough to identify, showing the growth of the hotspot over 70 days of time frame. If we continue the simulation, the hotspot will continue to grow bigger. However, 90 days is a typical wildfire season in Indonesia, and therefore it is reasonable to stop at this time. And the right figure shows the burn scar from the prediction of far side. So we kind of compare our model with the operational model. And it is clearly seen that this prediction is similar to the prediction from our model. This is the detail of comparison of the prediction between our model. We call it Capasto and Farsight when they are validated against the satellite observation. In this table, true negatives and true positive are the accurate predictions, where the predicted and observation both are burn or non-burn, so match. False positive correspond to predicted burn region but not burn in the observation, and false negative is the vice versa. So the area is predicted to be non-burn, but it is actually burned in the observation. We found that the accuracy of our model is 79%, which is similar to the accuracy of Farsight, 80% accuracy. We compare further using Cohen's-Kappa criteria that represents the degree of similarity. Both prediction have a similar value of Cohen's-Kappa. Our model with 0.57, it corresponds to moderate to substantial, and Farsight has a 0.61, which corresponds to substantial. We also validate our model in terms of burn area at the 3 different times when the satellite observation are available. At first and second time, on day 8, day 3, and day 8, the burn area from our model is very accurate with less than 5% different with the observation. But at the end of the Fleming lifetime, our model overpredict the burn area by 30%, around 30%, where the predicted area is around 11,000 hectares, and the observation is around 8,700 hectares. But this inaccuracy, I think, is acceptable because this is a landscape scale simulation, and it has a very high degree of uncertainty for the inputs. For the smouldering, the only validation that we could do is based on the number of smouldering hotspot at 3 different times. Total number of hotspot at the end of the simulation of the nucleation period after the Fleming stop in the prediction is similar to the observation with 15% difference. The highest discrepancy is on the 8th, where the difference between prediction and observation is higher than 40%. We argue that this discrepancy is from the spatial variation of moisture content that has not been considered in the model. This is because the spatial resolution of the data from the soil moisture model, the peat CLSM, is too coarse for the landscape under study to have spatial moisture variation. So its resolution is around 5 kilometers, and the landscape size is not that big. The increment of hotspot from day 3 to day 8 is higher than the increment from day 8 to the last day. So the difference between here and here are different, which means that the peat cover by the burn scar until day 8 is drier than the peat cover by the burn scar until the last day, which means that the moisture on those two regions are different. That makes that the increment of the hotspot is different as well. So that's why the spatial variation of moisture content is also important to get a more accurate result. We simulate the peatland wildfires in Borneo for 90 days. We split into 2 temporal regimes in the simulation, consisting nucleation and growth regime. Nucleation is the regime where the smouldering is dominated by the emission of smouldering by Fleming. So when the flame is still active, and the growth regime is the regime where the smouldering, the growth of the smouldering, the increment of the area of smouldering is dominated by the spread of smoldering. So after the flame extinguished, we found that both in nucleation and growth regimes, the smoldering burn area are increased exponentially with time, but this increase was slower during the growth regime compared to the nucleation regime. At the end of the simulation, we predict that 54 hectares of peat were burned. We also try to simulate the wildfire if we do not consider the temporal variation of peat moisture content. So for the simulation with temporal variation, we name it transient MC, and the one without temporal variation, we name it constant MC. The temporal variation of peat moisture in transient MC is shown in the red figure. This figure shows a weekly average of peat moisture, where the error bar are the range of daily variation. So in the model, the peat moisture is varying daily, but for clarity, the red figure only shows the weekly average. So it's not like we do not use weekly peat moisture, but still daily. For the constant MC, we use the peat moisture of the average value of the temporally varying measure, the blue line in the figure. So it is the average moisture content of 90 days time frame, and it was 83% the dry basis. Comparing transient and constant MC, the shape of the graph are similar in exponential increase. However, it is clearly seen that the increase of smoldering burn area in the constant MC case is significantly slower than the burn area in the transient MC. At the end of the simulation, the prediction from constant MC significantly underestimate the smoldering burn area, where it is only 12 hectares. That is almost 5 times smaller than the prediction from the transient MC. This finding shows that the importance of considering the temporal variation of peat moisture content for simulation of peatland wildfire. We further use the model with transient MC, so with temporal variation, to predict the smoldering burn area if it is nucleated over the same burn scar. So the burn scar of flaming is the same, but what if it happened in different months in the years from 2000 until 2019? Each individual case runs for 90 days. So there are a total of 240 cases. And the first case goes from January 2000 until March 2000, and the last case goes from December 2019 until February 2020. Each of the case has different temporal peat moisture content variation that were also estimated by using peat CLSM. And this is the example of the variation of peat moisture content from the peat CLSM. Figures show monthly data, but we still use daily, just for the sake of clarity. We found that the smoldering burn area in growth regime is linearly proportional to the burn area in the nucleation regime. So for a certain burn area in the growth regime, we map that with the burn area in the nucleation regime, and we found that they are linearly correlated. And the R-square value is 0.98. This means that the increase of smoldering area during the spread depends on the nucleation. So how many smoldering hotspots are ignited is the determining factor for the growth of the smoldering or the spread of the final burn area of smoldering. This finding is strengthened by the second figure, where the burn area in the regime decreased exponentially with the Molly average peat moisture during the nucleation period with the R-square of 0.93, but it is independent of the Molly average peat moisture during the current period. Therefore, the peat moisture during the nucleation period is the crucial factor determining the smoldering area. However, the maximum difference of peat moisture in this case is only 20%. So this finding may be not apply when there are very large difference of peat moisture. For example, when the peat moisture in the growth regime is very low, like a 0%. So the increase of burn area from the spread will become very significant, and the evolution in the burn area in the growth regime will highly depend on peat moisture in the growth regime instead of the nucleation regime. But this, if you said that, this is also unlikely because it will violate the hydrology process. Therefore, our findings remain valid. And then this figure shows the evolution of smoldering burn area from the nucleation regime, the bruise circle, over the 90-day simulation time until its final burn area, the red diamonds. From 2000 until 2019, there are many climate conditions such as El Nino and La Nina, and difference in their strength. We attempt to characterize the smoldering burn area for different climate conditions that happened between 2000 and 2019. The smoldering area varies significantly and range from 0 to 90, around 90 hectares. And the smoldering area is minimal if the flames spread in the wet season, so between November and May in Indonesia, and it significantly increased in the dry season. In the wet season, because of the relatively high peat moisture content, smoldering hotspots were less likely to be initiated or nucleated. So some cases have a smoldering area of 0 hectare. Meanwhile, in the dry season, the peat become drier and more vulnerable to the ignition or nucleation. These patterns prevail on most years, except in La Nina. When we have a strong La Nina or cold years, like the one in 2008, the smoldering area was more than 10 hectares throughout the year, regardless the season. On the other hand, during an El Nino event, smoldering area significantly increased, such as the one in 2015. This maximum smoldering area predicted for the duration of a strong El Nino was 93 hectares. And for a year without El Nino, like in 2001, it was only 48 hectares. So it's like almost double when we have El Nino. To sum up, we use Zero Automata for the first time to model field scale peatland wildfire with temporal variation of peat moisture content. And we show that if we do not consider the temporal variation of peat moisture, it will significantly underestimate the prediction of smoldering area. And we found that the regime of smoldering hotspot creation, so when the smoldering are still initiated, more strongly affect the fire's severity than when the smoldering starts spreading. We show that the smoldering burn area range from 0 to 93 hectares when the peatland start at different time within 20 years time window. And significant seasonal peat moisture variation that are affected by climate greatly determine the extent of smoldering wildfire. And findings and model can help mitigate peatland wildfires. Thank you.